Hello, everyone. My name is Asar Warbani, as mentioned already. Lead data scientist at H2O and working with our customers and partners on various data science use cases. And specifically at H2O, our focus is to make sure that these use cases eventually get deployed and go live. So that's really a crucial part of the core of the platform that we're working on at H2O, so that our customers that get the expected return on investment that they put in data science AI project. So today I'm here together with our partner Ankud to talk about some of these practical use cases that we have worked on with our customers in manufacturing space. With that, I hand it over to Carsten.
Thank you very much, Askar. My name is Carsten Schnapper, and I'm responsible for business development in the areas of data science and IoT at Ankud IT here in Nuremberg. And today we would like to share with you our insights and experience on how AI can add value to your manufacturing. And this is our roadmap for the next 30 minutes. First, I will tell you our view of why AI brings value to your manufacturing. Then we will go into 3 use cases and followed by a live demo from Ashka. And of course, with all the buzzwords, hypes, and highly praised technologies in the field of artificial intelligence, the question arises, why AI in manufacturing? And if we only let numbers speak, we see we have a loss due unplanned downtimes of 1.3 million euros per hour and per manufacturing alone in automotive industry. We have a loss of 10,000 euros per hour and per plane in the aerospace, and also 20 billion per year in the chemical industry. And the Wall Street store, in summary, of all industries, a loss about 50 billion euros. Wall Street Journal found out. And from our perspective, there's a big potential to reduce this cost and this loss with AI. But let's go a step deeper and look at the effects of unplanned downtime. Deloitte has identified 6 maintenance and error dimensions which result from unplanned downtime, and where it could be mitigated or eliminated with AI. At first, for reachability. There are more or less favorable times for the maintenance of a plant. Example here, maintaining a train overnight in the depot is easier than maintaining a train that has been stranded on a remote track during operations hours. Or cascaded damage. The failure of a single part can damage an entire system. For instance, here, an electrical discharge due to a defective capacitor can mean that an entire circuit board can no longer be repaired. And if you can predict this electrical discharge, then you can avoid this. Also, quality, a big topic in manufacturing. Systems that are approaching failure endanger the quality level of production. For example, glue nozzles that are becoming increasingly clogged may not deliver enough glue to ensure a permanent bond. And to avoid this, you can use AI to predict or detect when the glue becoming clogged. Also, equipment logistics. Maintenance requires preparation such as ordering services or using tools. As example here, broken gears can only be identified after opening the gearbox and must be ordered from the manufacturer while the system is shut down. And here, if you can detect this maintenance when the wear is there, when the wear increases, so you can also avoid this. Then here, interdependencies. Unscheduled maintenance can result in significant downtime and put productivity at risk. For example, here, maintaining a pipeline can bring subsequent production to a standstill. Also, at least, the failure of a system can directly or indirectly endanger the safety of the process. For instance, in the food industry, a broken food processing machine could cause fragments to get into the food. And if you can detect this or predict when such a tool has a different in certain level of wear, so you can avoid this failure. This was the 6 dimensions of maintenance and failure, written from Deloitte. And now, finally, here, as you can see, the zero defect manufacturing approach would be a way to meet such challenges just presented. The zero defect manufacturing approach has a goal to decrease and mitigate failures within manufacturing processes, and to do the things right in the first time, or in other words, to eliminate defect parts during production. But how we can achieve this? If we have a look on the slide, then we see that on the one hand, we are detecting errors in the product and in the process. For instance, through anomaly detection or image recognition, and for taking actions like repairing, as you can see here. On the other hand, we are predicting the degree of wear of tools in order to ensure a smooth manufacturing process and preventing errors. The zero defect manufacturing approach is not new, but the great thing is that new technologies and the amount of data available making implementing such an approach even easier and more scalable. But okay, that was our view of why AI and manufacturing fits perfectly together. Let's go forward to the use cases. Predictive maintenance. I think that's a term for nearly everyone, and one of the best known use cases for artificial intelligence. Therefore, I won't go too much into detail. In general, predictive maintenance is to do the maintenance at the optimal and right time. And as you can see here, predictive maintenance has a wide range of application, from predicting malfunctions of a variety of different engines, here left, or the future conditions of turbines, over the wear of tools like cutting knives from packaging machines, and the maintenance in vehicle fleets or stocks. And at this point, I would like to share with you a implemented predictive maintenance solution at our customer. The topic here was the early detection of the wear condition of a cutting knife of a packaging machine based on vibrations. And here within 1 week, we integrated a sensor that delivers the time series of the vibrations, stores the data in a database, and we developed a high quality model with H2O that predicts reliably the degree of wear. And currently we are in the process of bringing this solution to production that the end customer of our customer gains value from it with a better product at the end. And later, Ashka will show us a demo how we can implement an application for predicting the condition of failure of engines. But let's go a little further to the anomaly detection. Anomaly detection, also a wide use case or a big use case for manufacturing. Here you can see a real-world example how you can implement anomaly detection in production. What we currently do at our customer. The context is here, a manufacturing line with 12 processes, where we have 300 sensors and over 24 cameras. We have a wide range of data like time series, image data, and flat data. And the goal is here that we are detecting or predicting anomalies like cracks or defective solder joints and non-homogeneous glued areas. With the big benefit that we have early detection and ejection of scrap due to abnormal patterns in the production parameters. With the goal to reducing scrap, improve the product quality and the satisfaction of the end customer. And if we have a closer look to the architecture left, then we see on the first layer the production line as data source. From here, we are loading the data to topics in Confluent Kafka as streaming technology, which enables real-time data for our application. From here, we are loading the data to Travelers AI to build a high-quality machine learning model quickly and resource efficiently. The H2O own module format allows us to integrate the machine learning model directly into the data stream to Kafka. From here to here, this is a data stream, and here we're putting the module file directly in the data stream. That enables us a very low latency. So we can save the prediction directly to another Kafka topic, which we can then access directly from the hybrid cloud and visualize on the H2O Wave dashboard, and making it available to everyone on the line. And finally, our customer choose this technology stack with H2O Hybrid Cloud and Confluent Kafka because of the following main values. Hybrid Cloud is a one-stop shop which is simplifying the implementation, for instance, for machine learning development, deployment, visualization, and providing this application to the end user. The module format is suitable for real-time applications and also fine with the Kafka stream, and H2O, as I said, harmonize pretty well with Kafka. That was the description of how we currently implement anomaly detection at our customer. And in the next step, Ashka will show us a quality assurance with AI could look like. Ashka, the stage is yours.
Yeah, thank you, Carsten. Yeah, as pointed out, quality control and quality assurance is another topic, and actually the interesting one in manufacturing. And actually, you know, the point is that no manufacturer wants intentionally to deliver a faulty product to the end users, right? So we want, and that's not the only goal. You know, we don't, not only that, we don't want to deliver faulty products, but we want to detect any defects and faulty components, subcomponents as early as possible in you know, production cycle, right? So the idea here is that, you know, and that's why we have quality controls, quality assurances, you know, processes in place to make sure that, you know, we are delivering at the end of the day, you know, right product to customers with the quality that we expect. And the fact is that, you know, there are different processes, there are different tasks that we need to do to guarantee that. But one of these processes are inspections, right? So we do inspections, and many times like visual inspections, and many times, especially when it comes to visual inspections, you know, in order to look at, you know, the surface of the component or things that are produced, to look at if there is certain defects on it. And many of these inspections are done still today manually. And one of the drawbacks of manual process that we all know is that that's slow, it's prone to error because, you know, we humans, depending on our emotional state, depending on whether I'm hungry or tired. I might have a different quality, when I'm working physically in these topics. So anything manual tend to have errors depending on the we humans tend to have errors. Like so what we can do. The good news is that these days algorithms and in AI and data science became so good that if we provide a few examples on what a defective product is, or like component or the surface look like, as opposed to what a correct one would look like. So if you provide those examples to these algorithms, they can pick up the pattern of what a faulty components are and what not faulty product look like. So based on that, they could give us some ideas on whether that's a faulty or not, and if there is a fault, and also where is that specific defect, and can locate those for us so that we can do the further investigation if it's required. And the good thing here is that as opposed to humans, these algorithms and these models could run 24/7. They don't get tired. Thanks God, there's no unions for models and algorithms so far. They don't have any rights, so we can use them as much as we want. So that's the idea, and that increases the productivity. That increases, reduces the even the inefficiencies in the quality control process that we have. And one example here is that if you look at that board, sometimes soldering might miss one or some other points like this one. We have a missing hole here that that obviously is unwanted, but as you can see in that slide, one has been missed, and and visual inspection of these things are not easy for humans. So in order to just get an idea that how these types of use cases, and also some of one use case has been pointed out by Carsten around predictive maintenance, are prepared a demonstration to go through that and look at how we do these, how can we use algorithms to accomplish and do these kind of use cases. And with that, I'm going ahead and share my screen. And I guess, Carsten, you need to stop yours that I can. Okay. All right. All right. So I hope that everyone can see my screen. And what you see here is actually H2AI's hybrid cloud. And it's a platform that allows you from data, just starting from data, looking into data, visualize those data, creating models, putting those models in production, meaning that making those available to be used by applications, and to finally create applications like those that you see here inside that platform. So it enables us an end-to-end environment so that we can start from data, get to the point that we can have an application that business users now can use these applications like predictive maintenance and some other applications that we see here. One thing that I would like to present in today's is this example with printed circuits board that I had in that slide. So if you look at a couple of examples, I have a couple of faulty PCBs here, and can someone look at these boards and tell us that where are the problems? Probably it's not that easy and straightforward, right? So like this one, as the name of the file even suggests, we are expecting to see some couple of missing holes. I can see this one, you see this one, but let's upload that to that application that I've prepared. See how it can detect me for me. So it uploads. I mean, for this demonstration, I'm using the upload here, but actually in a real case, what we want to do is that streaming based on the architecture that has been described by Carsten into the application, so that in the real time we can have that kind of processing. So as you can see, the 3 holes has been detected here by this, and I could see this one and see one, but one might I might oversee. And there are even harder problems here to find out. I don't know, like this one, spurious coppers, when they leave, you know, they are very similar and not so straightforward to detect. Like this one, you know, even when it shows me that where the problem is, it's not so easy for me to know what really problem is unless I zoom in and see that, okay, here, you know, some part of the copper left that should have been removed actually, and the other one here. And the good thing here is that, you know, first of all, this is an application that I just, you know, put it together quickly, prototype on top of the model that I've trained by showing this model, you know, this algorithm, some examples of what a faulty or, you know, boards with defects look like, and, you know, which ones are correct ones. So, and with that, I, you know, trained that model and deployed that model inside the platform, and that's the endpoint that I'm using, that endpoint here and inside this application. And, you know, and that application eventually can be used someone from the business or someone that is a part of the quality control and, you know, inspect and doing this kind of inspection. And, you know, by able to do that process inside the platform in a short amount of time, I guarantee that, you know, the applications that I'm creating or the investment that I'm putting inside my data science team, they can reach the business units quickly, and they eventually can also give a feedback, right? You know, this one, for example, if it was okay, I could have like unchecked it and submit it so that my data science now have a, you know, an updated data that they can, you know, even improve the existing model based on that feedback. And that's quite important that, you know, data science team and AI expert has direct access to business users and, you know, end users, so that they have this, you know, feedback to improve these kind of applications. There are another application that has been another use that's been mentioned by Carsten was predictive maintenance. So this is another application that, again, I put together for the demonstration purposes here. As you can see here, you know, all these boxes here represent one equipment that, in this example, they are engines, and what they are doing, they're basically giving me the likelihood of whether that engine is going to fail in the next couple of days, based on the sensor data that are streamed from these equipments and run over the models that I've trained and deployed inside the platform. So the sensor data goes to these models, and the models predict whether they are going to fail, and, you know, whether they are going to fail, you know, soon or you know, in a couple of weeks or something like that. So, and they are giving me, based on that information, whether we are in warning stage or failure status. So, and that's the idea, right? So, and specifically in these scenarios, when we are going to predict whether something is going to fail or not, we know that it's not enough for me to just know whether something is going to fail or not. Which in this case, like here now, you know, I can look at in this specific engine here at a different point in time, and it'll look at what is the prediction at this specific point, right? And the point is that when I know that something is going to fail, actually my engineers perhaps want more information. Why this, you know, why the model predicts that? What is the reasoning behind it? So for two reasons, perhaps first, to trust the results, the predictions or the outcome of the model, and second, to have a starting point for the repair or maintenance that they need. And in this information, in the world of, you know, in the terminology of data science, we say machine learning interpretability. So we want to interpret the model. So then why this model specifically did that predictions. And what you see here on the right side is actually one of those interpretations that comes out of the model. And also there's the platform built in a way that when we train a model, we also produce this interpretability, so that when a model predicts that this is going to fail, we now have some reasons that, you know, where to look at. Like in this predictive maintenance example, we know that sensor 11 maximum amplitude and sensor 4 maximum amplitude reached the point now that perhaps causing that the fact that at least the model believes based on these information that it's going to fail. So now our engineers can use this information, having a starting point for performing maintenance or further investigation if required. So, and that's basically two applications that we've seen here that are implemented, created application and run in that platform. But you might ask your question, okay, how I do start? How the workflow look like if I wanted to start with my own data to go and create an application like this? So in order for me to go and create one, I go back again to the platform. So this is the H2AI Harbor platform, as mentioned earlier. I need to start from AI engine. AI engines, as the name suggests, are engines that allows me to create now models when I start from the data sets. And Driverless AI is one of those engines. Basically, it's an automated machine learning platform, which basically automates many steps of the process that data scientists need to do to create those models. So, so this is a couple of data set that I put it into the, I uploaded in the platform. This is for predictive maintenance use case, as you can see, and these are sensor data. So, in principle, when I get the sensor data, I can, download it here, and in that data set, I also have a remaining useful life of those equipment. So with this, I'm going to train a model that can predict for me, based on the sensor data, what would be the remaining useful life for the in the future, right? Another point that I would like to mention here is that this is more or less agnostic to the type of the data set. So I could use image, I could use text data set, depending on what type of data set I have. I could, basically start building my models for that, fault detection in that, on surfaces or things like this, if I wanted to build those kind of models. Now, so what I need, and again, this is an AutoML platform, meaning that, I don't need to be, go into the nitty gritty of, what kind of algorithm I need to choose, what I need to do. I can simply start from the data and predict and, specify my objectives. What is my objective here? To predict remaining useful life of that equipment. I have some options here if I wanted to use, like drop some of columns that, for example, when I don't have it, there are certain data set here that I won't have at the time of prediction, I need to drop those. And I'm going to drop those and do some certain settings here. These settings are there that if I'm an expert data scientist, I want to go into the under the hood and do lots of stuff and certain settings that I think that works best for this specific data set, I can do that. But this comes with the default setting based on the data set, based on the objectives that I've set, and these are set in order that I can already get a very good result. Right, so I don't need to really do much. As soon as I specified the data set, I specified my objectives, that's it, the only thing that I need to do. The rest, I can launch the experiment and let the platform build the right model for me for this specific use case. And the idea here is that, what platform now does, it looks into the data set, figures out, okay, what kind of algorithm might be helpful here, what kind of transformation on the data set needs to be done so that we can get a good results here. So all these steps that typically needs to be done also manually and previously, by data scientists spending time on, okay, what kind of algorithm I need to use here, what kind of transformation I needed to do. So these steps that typically we did it in the past manually, now they can be automated. And now we can spend our time on more intellectual part of the process, like thinking about data, what kind of use cases I can solve for business, and have more time to think about those steps rather than the manual tasks that actually can be automated, right? So that's the idea here. And this is going to take a little bit of time until it finishes. Until that, either I can go grab coffee and wait until that finishes, or we can continue and look at one finished experiment. Any experiment that I build here, I have those lists here. I can go and do some investigation. How good they are, and did I build a good models here? And those kind of process, right? And after that, when I'm sure that this is the model I want to use it, this is one I want to deploy it and go live, then deployment is quite straightforward. Now I can go back again to the platform and go into my model. Any model that I built here in the platform, they became available in MLOps part of the system, where I can see all the projects that have been done, the models have been created. And this is an example again for this specific application that we saw here, right? So this is this one. Now, I can simply, any models that I've created, I can see it here, and I can go ahead and deploy that in live system, right? And as soon as I deploy those, a REST API becomes available, so I can use that REST API to integrate with my other applications. And if I have a pipeline, like like the one that Carsten mentioned, you have it, you stream the data, you get the data from the production line, and then I can run those data through that and get the predictions that I wanted. That's the idea. And why this is useful, because what we have done here, from creating the models here, all being automated, easily can I create the models and go here and deploy those in here, all being streamlined. Meaning that there is no manual code I've written. And so when it comes to deployment, now IT is very happy because they are not receiving from me, spaghetti code or something like this, or even if I'm writing a nice, neat code, sometimes not according to the IT standards, right? Sometimes even Python and things like this is not part of the standards in IT. So I need to rewrite it in a language that IT allows me to deploy, or they're going to have that deployed. And as a result, when everything is streamlined like this, IT is going to be very happy, because what they need to do, they just see in their dashboard, okay, a model is now available to be deployed. They review if the review needs to be done as part of the process, and clicking here and deploy that in live, and everything here is monitored. If there's a data drift, if there is anything goes wrong, they have a full monitoring system in place to go and investigate. And and the next step is the creating now. So now I've created my model, I deployed it. Now I have an endpoint like this to use it in my application. Now the only thing that is left for me to go and create or a prototype in an application, a web application like this, that I can run and deploy it in the platform. For that, we have a Wave framework, which is even open source. I mean, you can go and start right now to use it for your applications that you have in your organization. So you can use this Wave framework. It's an Python SDK, which allows you to create applications like predictive maintenance and the other one that I've presented today quickly in a short amount of time. And it's a low-code framework. You don't need to know HTML, CSS, or JavaScript to create those applications. You're really just a Python code, and you can create applications like this one or this one in a short amount of time, putting these components together to create an application, so that the business users could quickly have access to the models that have been created by AI teams. So that's very crucial, because we know that AI now is kind of new for many organizations. This is like most of the time is part of innovation programs and organizations, meaning that we are innovating here. So with anything that we are innovating here, it's important that we get quick feedback from the end users, and it is important that in a short amount of time we reach to the end user and get their feedback, whether that is something useful, is it something that we want to deploy, is it something that helps the organizations. And this streamlining and having a framework that allows us to quickly create those applications and make it available to end user to collect the feedback and, you know, improve on top of that, and you know, make the innovation part of the organization's you know, day-to-day work. So that's the idea of that platform, and that's all I wanted to show today to you. So back to you, Carsten.
Thank you very much for this impressive live demo. Now I share my screen. Now I would like to briefly summarize the last 30 minutes. I think we can say it's a perfect time to implement a AI-driven manufacturing approach, because we have such platforms like H2O with the right algorithm. We have enough enough data to train them, and we have high-performing hardware to execute them. Predictive maintenance, anomaly detection, and quality assurance with image recognition are proven use cases which have been implemented many times. And an end-to-end AI platform is better as a standalone solution because it has a shorter time to market for your AI application. So I hope we have made you curious for using AI, and could you courage to create your first POC in manufacturing. So try it here. You have a 40-day free trial at h2o.com and try it by your own. Thank you very much. And now, if you have any question, don't hesitate to ask us.
Thank you both. Very great presentation today. The link is h2o.ai, not .com, sorry. But I'll put the link in the chat again, so you can follow the link. So as we said, if you have any questions, please write them in the chat box or in the questions tab. We did receive a few questions already, so I'll ask the first one. Can H2O's platform be installed on premise?
The answer is yes. So that's a hybrid platform, meaning that, you know, either it can run on cloud or on premise, depending on you know, the preference of the customers.
That's also what we are doing at our customer currently, because we know the issue or challenges of a manufacturing plant, and so it's very important that we can also integrate this on premise at our customer.
Great, thank you. Another question came in. What are the model deployment options? For example, can we deploy H2O's model on edge devices?
Yeah, that's a good one. And the reason that why I'm saying that's a good one, because there is lots of, you know, depending on, so where we want, you know, what are the preference of the customer, what is the environment, because, you know, the platform is very flexible on that. And you know, the example that we saw today was based on deploying on MLOps, where it exposes REST API. So now the question is whether REST API is useful solution for us. Can we use that? Because the advantage of that approach is that I have a full you know, monitoring in place. And then there is another way that if you already have a you know, deployment pipeline, the great thing here is that you can export the models in different forms, whether you want to run it on Java environment, R environment, or Python environment, depending on the, you know, what kind of runtime you have. You can export that and run your the models, and also the entire, you know, feature, you know, engineering process, the entire you know, pipeline can be exported and deployed in those environment. And one of those environments obviously could be an edge device, which is not atypical when it comes to manufacturing.
Okay, thank you, Asghar. Is stream processing possible?
Is stream processing is possible? Yes. And again, the reason that why it's possible, because you can export these artifacts and ingest it, you know, and put it in, you know, like in Kafka. Carsten has shown us one of the architecture that's being used by one of the customers. And some are, streaming pipelines, depending on what kind of streaming pipeline I use. Can they use like Java? Many of those that actually support Java or C++, so they can run those, or even Python or R. So yeah.
Okay.
Okay, I see that event froze. I don't know if that's me or for everyone, but I can see that there's a question. There's a question that says that what is the process of monitoring incorrect prediction given by the model? And is this feedback into the model to retrain the algorithm? So if I understand that question, the idea here is that how we can get feedback when we get, in that specific PCB fault detection example that we saw today. The question was that, how we can get that feedback, from the end user back to, so that we can improve it, if I understand the question correctly. So the idea is that, yes, and in that example, we saw that, in the right pane, I put exactly that specific feedback, because that's actually one of these, is a very important topic here, because when you deploy your model, no model is going to be at the start perfect. There are many statistical approaches here that, and on average, they are going to be good, but not every case. To improve these models, you need to get that feedback. If they made a mistake, you need to provide a means. If they have an interface, you can easily embed those feedback options that end user can give feedback. Okay, that was not correct, and these feedbacks could be collected, and basically you update your training data set based on the new data set, and you can update it. And how you are going to update it, it depends a little bit on the use cases, whether you are going to do continuously update those, or you need to retrain it. Depends on the algorithm and the use case, then how you can do it. But yeah, that would be possible.
We still have one question regarding driverless AI. The question is, do we need to pre-process our data before uploading it? Ashkar.
Yeah, it depends on what pre-processing meant here. Obviously the tool is not an ETL, so anything that related to ETL needs to be done beforehand. But if the idea is that, because some of the pre-processing that data scientists do, like, they do dimensionality reduction, they do imputation, they do, all of, lots of these kind of feature engineering processes. These steps are automated in driverless AI. So again, if it meant things like, creating new features out of the existing features, these steps are automated. But if the idea, if the question directs to ETL, no, it's not part of the driverless AI. The ETL needs to be done separately.
The next question is, have you got any applications in real-time optimization driven by AI? The use case with the anomaly detection I showed you, that is, there's a goal to do it in real time at the end. Currently, the whole system, the whole application is deployed in the plant, and the Apache Kafka system is deployed in the edge directly on the manufacturing line. The goal here is, if we have an anomaly, we want to eject this product directly as fast as possible in the production line. So yes.
Great. Thank you, Asghar and Karsten, for taking the time today. I don't think we have any other question. Thank you, everyone who joined us. You can see here the contact details for Asghar and Karsten, so feel free to reach out. We hope you enjoyed the presentation. Stay tuned for upcoming events and have a great rest of the day. Thanks, everyone. Bye.
Thank you, everyone.
Thank you.
Feel free to take a screenshot for that as well, to make sure that you have the contacts.
Great. Thanks, everyone. Bye.
Bye.